Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together.
One of my favorite rules to help save me from memorizing a bunch of other rules is indeterminate forms with L'Hopital's rule. I really find this very, very useful, so make sure that you can use L'Hopital's rule before you just use it generically. It must apply first. So it must be an indeterminate form before you can start doing L'Hopital's rule. So what is indeterminate? What is the requisite for us to have L'Hopital's rule? If you do the limit as x approaches the value of f of x over g of x, and you get 0 over 0, or you get infinity over infinity, then and only then can you apply L'Hopital's rule. Those would be indeterminate forms. So the rule, L'Hopital says, hey, instead of doing that, since you get an indeterminate form, what you can do instead to get that limit you can instead do the limit as x approaches a of the derivative over the derivative. Okay, so what does that mean? Well, let's look at the limit as x approaches 0 of the sine of 4x over 8x. If I were doing this before, what I would need to do is I would need to look at this as the limit as x approaches 0 of 1/2 multiplied by the sine of 4x over 4x. See how it's still the same problem because 2 times 4x is 8x. And then remember that there was a rule that says that equals 1. So this would be 1/2 times 1, or 1/2. L'Hopital is going to not make us do all that. Okay? So if I were to substitute 0, I'd get sine of 4 times 0, which is the sine of 0, which is 0, over 8 times 0, which is also 0. So L'Hopital's rule is going to apply because we have an indeterminate form. So instead of doing the rule and memorizing some poor rule, we're going to, right, change it to the limit as x approaches 0 of cosine of 4x, don't forget your chain rule, times 4, over 8, because the derivative of 8x is 8. So we're not doing a quotient rule. It literally is the derivative of the numerator over the derivative of the denominator. So let's check that out. Cosine of 4 times 0 would be the cosine of 0, which is 1 times 4. That's 4 over 8. And 4 over 8 is definitely equal to 1/2. So L'Hopital saved us from memorizing a rule in this case. So if you were memorizing that rule from earlier in the calculus year, can L'Hopital replace it for you? Absolutely. You just have to make sure that you have an indeterminate form before you do it. Could you check it graphically and kind of do the squeeze theorem? Absolutely. You could test 0.00001 and negative 0.001. That would be fine. Okay. So what about now with this? Of e to the x over x squared. Well, we know e to an infinitely large number is infinitely large, and infinity squared is still infinity. So we have an occasion where L'Hopital's rule exists. So limit as x approaches infinity. The derivative of e to the x is e to the x. The derivative of x squared is 2x. E to infinity is infinity. 2 times infinity is infinity. Again, indeterminate. L'Hopital's rule still applies. So let's again L'Hopital this out. The limit as x approaches infinity of e to the x over 2. Okay, well, that would be e to infinity, which is infinity, over 2. And infinity divided by 2 is still an infinitely large number. So now we have our limit. It's an infinite limit. So this saves us from having to do, falling back to other methods if we need. Okay? Now, it's really important that you understand that this is going to be an exact science and we're going to get true exact values. So the limit as x approaches 0 of 8 to the x minus 5 to the x over x. Okay, well, let's check. We know the bottom's 0. 8 to the 0 minus 5 to the 0, that's 1 minus 1. That is also 0. So, yep, it applies. Alrighty, so the limit as x approaches 0. The derivative of 8 to the x is 8 to the x multiplied by the natural log of 8 minus 5 to the x multiplied by the natural log of 5 all over 1. Okay, so it's over 1. There we go. Now it's going to work out. We're fine. We've got this. Okay. So substitute 0, we get the natural log of 8 minus the natural log of 5. There we go. That's our rule. We could also say the natural log of 8/5. But now we have our limit. The limit as x approaches 0 from the right of x multiplied by the natural log of x. Now, why is it important that it's from the right? We know the natural log of 0 does not exist, so I cannot substitute it. But you might be going, well, we're up the creek without a paddle. L'Hopital's rule doesn't apply. You're right. It doesn't at this point. So how are we going to find this limit analytically without a calculator if we can't do it? We can still use L'Hopital's, we just need to get creative. L'Hopital's is meant to be a quotient. That way we have a numerator and a denominator. So right now this is over 1. So what would happen if I divided by x? Which is the same thing as multiplying by 1 over x, right? I would get natural log of x, I won't worry about it writing it like this, over 1 over x, or the natural log of x over x to the negative 1, either way. Now, substituting 0 into both of these gives me undefined over undefined. It's now in an indeterminate form. Now I can do it. The limit as x approaches 0 from the positive side of the natural log of x over x to the negative 1 is going to equal 1 over x, right, divided by negative 1 x to the negative second. All right, let's think about what that equals. 1 over x divided by negative 1 over x squared equals 1 over x multiplied by negative x squared over 1. That equals negative x. Okay, now I forgot to write the limit as x approaches 0 every time. The limit as x approaches 0. The limit as x approaches 0. I'm running out of room here. So what we're really looking at is the limit as x approaches 0 from the positive side of negative x. And if I substitute 0 in for that, I find out that it's approaching 0. So if you don't have a numerator and a denominator, sometimes you can still use L'Hopital's form if you can't just do the straight analytical derivative, so that you can go ahead and find it analytically without needing to resort to kind of typing it into a calculator and getting closer and closer and closer. So L'Hopital is very powerful. Just make sure that you match the rules required to have L'Hopital with you.
Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? And drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.